Thank you so much for having me. It's been fantastic witnessing the future in the making. But for this morning, let's take a step back and talk about what some may refer to here as conventional analyses. I have the somewhat impossible task to talk about the landscape of current and coming cosmological surveys. I can't do that justice in 45 minutes, so I decided to pick some examples from a collaboration where I know enough and know what I can share, that hopefully I can also point to some useful lessons and things that went wrong. And because I want this talk to be useful for you, I'd like to invite you to just ask questions anytime. So let's get the landscape of galaxy surveys out of the way at the start. You've all seen timelines. I've made enough forecasts, and many of you may have done so too, that I will not dwell on particular forecasts, how well some coming surveys will do on the equation of state. But let's just start with imaging, and in particular here, weak lensing surveys, where right now we are still in the era of analyzing data from three surveys, I would say in friendly competition: the kilodegree survey, like energy survey, and hypersum prime cam, all following slightly different strategies in terms of survey area, indicated by the squares here, versus survey depth, shown there in number of galaxies per square arc minute. And the analysis that we're doing right now, and really learning from each other, completely built on lessons learned 10, 15 years ago from CFHLS, Cosmos, and the Deep Lens survey. They really did cosmic shear with for order 1 million galaxies or so for the first time, and we would have a really hard time getting started without lessons from them. In a similar spirit, right now, this is our boot camp to learn to do cosmology with 100, 200 million galaxies, so that then we are as prepared as can be for the next generation of surveys, where data in part is already coming to our hard drives. That's Euclid, Rubin Observatory, and Roman Space Telescope. On the spectroscopic side, we've been learning many of the lessons for the cosmological scale analyses from BOSS and eBOSS. Right now, we are in the era of DESI, Dark Energy Spectroscopic Instrument, and soon Subaru PFS. Very much looking forward to it. Both of those are fiber-based. And then the Euclid collaboration as the first collaboration dealing at scale with slitless spectroscopy and all the lessons in terms of systematics that entails. Hopefully, very much looking forward to their first results, so that hopefully we can implement some of that then for Roman Space Telescope, which also uses a GRISM. And that's what's currently on the horizon. Of course, different continents are already talking about the next generation of surveys after that. Now, with all that data, we want to do observational cosmology. And just to briefly also mention, of course, a lot of our constraints come from the expansion history, which is based on measuring the distance redshift relation using either standard candles or supernovae or standard rulers. That is the angle subtended by a known scale for cosmologists, the size of the sound horizon, either imprinted in the cosmic microwave background or imprinted in the distribution of galaxies, shown here as in the galaxy 2-point function from DESI. And comparing these two, the BEO scale in the galaxies and the CMB gives a surprisingly good agreement, telling us that, yes, something in our cosmological model works really well, but it's getting interesting. So I'm showing that here I'm not very, in a way that's not as easy to read off. In the deviation here from the lambda CDM scale fitted to Planck. In the most recent results, there's a year 3. You can see here the constraints on H0 and omega m from the different DESI subsamples, and then combining with the CMB and supernovae various samples into the dark energy equation constraints that we've been talking about here all along. So that's the equation. That's the expansion history. Focusing more on probes close to what this collaboration is gearing up to, growth of structure. Idea here is that gravity drives cosmological structure formation, while dark energy, or whatever it is, slows it down. And additionally, we want to use that the inflation and relativistic degrees of freedom, like neutrinos, impart characteristic scale dependence in the distribution of galaxies, which we can then also use to put additional constraints. And here we then really have to take fluctuations that were of order 10 to the minus 5 in the early universe into the distribution of galaxies that is halos with overdensities above 200 today. So that is quite a modeling challenge. How do we do that in practice? A textbook would tell you that the variable for cluster structure formation is the density contrast. That's great, except that it's not directly observable. So we need some more traces. And you've already heard about halos and galaxies, briefly mentioning of lensing, and the two Z effects in previous talks. So these are the type of measurements that we want to use to then infer how structure is growing and what the cosmological model is. These observable traces are all subject to different astrophysics, as you've already heard in the LTU talks yesterday. So we want to combine them and get the best possible constraints, both on cosmology and astrophysics. Now, how do we get the best possible constraints? Of course, we want to combine or jointly analyze and then self-calibrate astrophysics and cosmology. For the expansion probes, that is fairly easily done. One can basically download the likelihoods of each individual survey and multiply them and arrive at these beautiful joint constraints, because these are independent probes. So that can be done fairly easily. If we now talk about structure growth traces, of course, these are inherently correlated because we may measure weak lensing and say TSZ or KSZ in the same footprint. So there's a structure formation correlation. There may be shared astrophysics, and there may also be shared observational systematics. So we can't multiply likelihoods anymore. We need to do a joint analysis. And what that joint analysis will look like, of course, then depends on what approach you follow. I'll be old-fashioned here. I'll just use summary statistics and an explicit likelihood, so that at the end I get my posterior on some parameters of interest. And that can be cosmology or astrophysics. Bayesian analysis doesn't discriminate, given some data vector. And then we have our explicit likelihood and marginalize out some nuisance parameters. Easy enough. But when you want to do this in a big survey calibration, there is still a lot of work to do. One aspect is the nuisance parameters, which we need to decide on as a calibration. And these will typically outnumber cosmology by far. When I first joined DES, I went to the different working groups and asked, what systematics are you worried about? What should we marginalize over? And in the end, they came back to me with a list of 1,000 parameters. That's not much by your standards, but in this case, that becomes rather intractable. Additionally, we will probably want priors on some of those parameters, and we have to go to either simulations or external data to calibrate those. Then once we've decided on the model, on the parameterization, we have to write down a model for our data vector that is consistent across all the different elements. So we need a consistent parameterization, say, of photoz's across the different working groups of the survey. That's really the realm of diplomacy, because in the past, those were cloistered working groups. And then we also get into the realm of perturbation theory, typically, because we have to take care of the structure formation correlation between the different parts of the data vector. So we need covariance. That's a big matrix that's not even block diagonal. And typically, one will use some kind of mix of perturbation theory and MOX. All right. Takes a few hundred people to do this, but let's go. As warm-up, I want to talk you through the mainstream DES Year 3 analysis using 100 million galaxies. Here we do combined probes in the sense that we do both weak lensing and galaxy clustering. We have a sample of about 10 million lens galaxies with fairly good photosis in the foreground. And we have 100 million source galaxies split into 4 redshift bins. And from those, we measure cosmic shear, galaxy-galaxy lensing, and galaxy clustering. And then we build a joint model to infer how structure is evolving over the redshifts probed by the Dark Energy Survey. Of course, everything starts with a plan. Here is our initial Gantt chart, way too simple. It expanded massively in the meantime. And fortunately, we had a team of 4 people really tracking that all those connections were made, that assumptions were consistent and everything. But at the end, we got this beautiful pipeline created or described here by Jesse Muir and Alex Amon. Starting out, of course, with photons coming into the telescope. They get converted into images. And at that point, we separate out the stars, are left with galaxies. We weigh them, that is, we do weak lensing measurements. We also have to measure their photometric redshifts, and then combine them with information from simulations and theoretical models, sort in the covariance outcomes parameters. In practice, of course, that is then detailed in 30 papers that describe algorithmic and model improvements in all analysis stages compared to DES year 1. And here's another beautiful flow chart from Alex illustrating all the different types of information that go in there, starting out from wild field images and deep field photometry, so that through image injection we can characterize the survey selection. And then in the next step we go through redshift calibration to redshift distribution. We have to characterize a bunch of systematics until we get to shape catalogs and blending and calibration. And then at that point, it, I guess, may enter the realm that's more familiar to most people in the room here in terms of, yes, we measure summary statistics. We have to decide on our methods and analysis choices. And in the end, we get to cosmology constraints. I will not go through 30 papers in 30 minutes. Let me focus on some of the modeling aspects here and validation, because I think that might be most relevant to this group. So we do 3x2 point here. That is excluding galaxy clusters, which were responsible for a good fraction of the 1,000 systematics parameters that I told you about initially. But compared to the wish list of DES before data, we made it even simpler. In the end, we analyzed 3x2 point data here using just 15 parameters for astrophysics that relate to galaxy density and galaxy shapes to the matter distribution. And you can think of these as pretty much the simplest models there are. And additionally, we have 13 parameters characterizing observational uncertainties, that is the redshift uncertainties for both of our galaxy samples, and then multiplicative shear calibration. Now, that's a pretty short list. And before we trust our constraints, we have to really stress test this model. First of all, this list of systematics is known to be incomplete. There's a bunch of systematics that we decided we don't want to deal with. And that means we remove contaminated data points where those systematics are relevant, and in the process throw out most of our signal to noise. Well, it works. And additionally, of course, this is our choice of quantization, not some actual statement about the actual behavior of galaxies. We don't claim that galaxy bias really is stepwise constant in redshift. That's just what we do here. And then we have to do some homework to make sure that these parameterizations are sufficiently flexible for our analysis. Now, dealing with these known but unaccounted for systematics is a tedious process. We figured that baryonic feedback and modulations in meta-power spectrum will be the main systematic for cosmic shear, and nonlinear galaxy bias for galaxy clustering and galaxy-galaxy lensing. So at that point, we agreed on some type of contamination that we put into synthetic data vector and analyzed them repeatedly, throwing out data points until our systematic biases are below some threshold. I would like to mention here that, of course, at the end, whatever scale counts we arrive at is not a unique solution. And you might be noticing there in that process a competition between systematic biases if you include too small scales, and your data becoming too unconstraining if you throw out too much. And then your posterior becomes skewed by projection effects. So you again have a systematic bias, but in that case, just from projection effects, not from astrophysics. But in the process, we produce a lot of plots like this, comparing what happens if we analyze our baseline synthetic data vector compared to one that includes baryonic effects and nonlinear bias, and then make sure that the offset between these two here is less than what our accepted threshold is. I should briefly point.
So, given that the constraint size doesn't really change, why would you even consider adding the contaminated part? It might be more aggressive if you think you can reduce the error bars.
I have not shown here that the error bars stay the same.
Oh, those are not error bars there, the ellipses?
Those are 0.3 sigma regions, but at fixed scale cuts. So both the baseline and contaminated data vector here are analyzed with exactly the same scale cuts. Because as we remove more data points, our baseline analysis will drift away from the fiducial due to projection effects. So we always need this comparison of the same data points with and without contamination to understand how much of it really is systematic bias, which one is an artifact of marginalizing in a high-dimensional parameter space. So that's quite a lengthy process. In the SGA3, I think we ran about 300 chains in total. For the SGA6, the collaboration went through multiple versions, each about 200 chains. One of my students right now is finishing an analysis going to small scales, for which he has run well over 1,000 scale cut chains. So this is one point of the analysis where data vector emulators can be extremely useful, even if they are somewhat approximate. After these scale cuts are established, then it's time for further validation. And in that process, mocks are really essential. For the SGA3, we relied on the Buzzard version 2.0 simulations led by Joe DeRose. This is based on AdGalds and then includes survey-specific systematics, photometry, and photometric errors. And in the end, we can then really reproduce the color-dependent clustering for our galaxy selections and the other parts of the data vector. So up there, you can see a comparison between the actual Y3 data shown in dots versus the Buzzard predictions. And we had 18 of those on which we run our DS analysis. And here you can see again the mean from a synthetic data vector, so the theory generated, versus running on mocks. That's an essential step of validation here, because for some parts of our data, that lets us test the choice of prioritization in the systematics model. For example, in Buzzard, of course, galaxy bias will evolve with redshift. It's not a stepwise function. But of course, we can only test those things that are in the simulation. For example, intrinsic alignments are not part of the simulation. That would require very different mass resolution. So we need additional tests then to make sure that those prioritizations are sufficiently flexible. And a lot of those tests then have to happen a posteriori, where we just say, okay, after we've analyzed, we check that our redshift evolution is fine comparing different models. Of course, it's important to determine this list of tests a priori to know what we want to check, so that we are clear about all assumptions. And I just want to stress here that the redshift evolution of systematics is especially important for dark energy constraints. And that's something that needs to be tested carefully, because sometimes the calibrations, say, that go into a simulation and which redshift that is done may impact the validation. Okay, after we've done our homework, we then present marginalized cosmology constraints, shown here in omega m and S8, marginalized, of course, over the rest of cosmology and those 28 systematics that I introduced earlier. And you can see here that cosmic shear and clustering and galaxy-galaxy lensing are consistent. So we take that as additional hints that our model is sufficiently complete so that we can combine and arrive at this 3 cross 2-point cosmology shown here in black. Okay, at this point, we've done survey, we've done cosmology, we've gotten our constraints. And the question then, of course, is how do we compare? Here is a fairly current overview of stage 3 weak lensing results, from CMB lensing combined with BAO shown here in the red contour, and 2 collections of current day cosmic shear constraints. So overall, these are fairly consistent with, I think, still most of weak lensing somewhat skewing to low SH compared to Planck, but that's an evolving topic very much under debate. You will probably hear more about that in the coming months from DS and then soon from other surveys. But the main thing I want to highlight here, rather than the actual constraints, is the process that leads to this. Yes, these are all, of course, results by different collaborations, but we did not get there in isolation. We come to this year 3 data analysis from the ES, also thanks to lots of interaction with kids and HSC, and that exchange between collaborations and reanalyzing each other's data has really been essential to understand our analyses. So that is something that I think can't be stressed enough, that these cross-checks across the community are incredibly valuable. And I would like to encourage people thinking about SBI to really think about how that will be possible. Because at least we have learned so much. Now, that all looks great. Of course, the idea then is that if we have these consistent results, we can combine them to obtain tighter error bars. But at times, we may also end up in situations like this and have to ask ourselves, well, have we found new physics? Is our model truly incomplete, or is it just unknown systematics? And of course, we all do these consistency checks all the time. Here, I just want to highlight 2 cases where we found surprising results to illustrate the process, and maybe having these offset contours helps to remember that these checks are really important. So let's start with our original unblinding of DES year 3, where we're still using a different lens galaxy sample. So at that point, we had rather inconsistent cosmology from cosmic shear and galaxy-galaxy lensing plus galaxy clustering. When we unblinded that in the telecon, there was a moment of silence, and followed, of course, by lots of chatter and people speculating. We've worked on that for a long time. Shivam over there is probably one of the experts on what we called X-lens, as just the X-factor modulating clustering. But one of the useful things that we realized in hindsight is that we can find this in the data. So we've been using posterior predictive tests to compare different parts of the data in data space. So what you see here is the prediction for galaxy clustering conditioned on galaxy-galaxy lensing and cosmic shear. So the model is fit to something that's linear in the galaxy density contrast, so that a lot of galaxy clustering systematics will average out. And you can see then that conditioned on cosmic shear and galaxy lensing, we underpredict what's happening in the data, suggesting that there may be some kind of systematic in that particular lens sample. That's a test that we could have done before unblinding, but we didn't think of it. We only thought of checking that cosmic shear and galaxy-galaxy lensing plus clustering are consistent. So those 2 contours over there that don't work in this case. But now that we realized that, yes, we should have included this in our unblinding list, we then proceeded with an alternate lens galaxy sample, which is basically just a magnitude limit selection. And because we had not unblinded that, when we found, well, those inconsistent contours, we could still extend our pre-unblinding checklist to include this PPD test. And based on that, we were then able to say before unblinding, we again have this mysterious clustering systematic in our highest redshift bins, but we conclude that these 4 lowest bins are okay. Now, of course, after this, the collaboration went overboard, and we have a lot of PPD tests for DES year 6, It's a bit searching under the streetlight situation, but of course you learn from every analysis. So as you go through this, of course, keep your eyes open what other collaborations are finding. Next one up, an unbinding telecon where people looked even more shocked, I think. This was the SU1 clusters using cluster number counts and a small-scale mass calibration from basically one halo-term cluster lensing. That had been validated to some extent on simulations beforehand, but when we originally unblinded the gray contours there, we lost half the matter in the universe. Not that great. Again, we did our post-unblinding consistency checks, now predicting as a function of the richness on the x-axis what the observed number of clusters or cluster mass should be if we assume the cosmology of the 3-cos 2-point analysis. And at that point, we find this is clearly a richness-dependent effect, with the lowest richness clusters being off. This turned out to be a selection effect due to projection effects, that is galaxies that are falsely associated with cluster members. And that's something that was not fully included in the simulations at that time. So of course, if it's not in your simulations, you can't validate it with mocks. We figured out what was kind of going on in 2020, but it's taken until probably next week or so to get the update showing how to finally do this properly using a simulation-based forward model. So more than 5 years in the making afterwards to include this properly. All right, after that detour on consistency checks and some things that can easily go wrong, let's continue with our survey cosmology and asking now, what do we learn about DS8 tension? How do we measure up to Planck? So here's our DS 3-cos 2-point combined results again, compared to Planck analyzed within the DS priors in green. And the answer is eh. So we have about 1.5 sigma or P of 0.13. Nothing to write home about. But of course, we're just in boot camp. We continue. And that is, in our future, are the options of modeling systematics better to include more of those small scales. We can combine more probes. And of course, eventually we'll observe more galaxies. So let's talk about modeling systematics better and information gain or not from small scales. I must say this is probably my favorite plot of the S3 analysis, even though you should not trust any of the contours, but I find it very illuminating. So Anthony Lewis, who's not part of DES, reanalyzed our year 1 data. In gray being the standard result, then in red, what happens if he fixes all the systematics to their best fit values. Of course, that's not a proper Bayesian analysis, but we can still learn what the potential gain would be if all our current systematics were constrained perfectly from external data. And then he also threw in the scales that DS had eliminated due to systematics contamination, showing that yes, there's more signal to noise. And if we were to get away with the same systematics model, that would correspond to massive gain in constraining power. So let's try to recuperate some of that information from small scales. And that is, we now have to include baryonic effects on the meta distribution. I don't need to tell this room that different feedback models predict rather different things happening, and in particular also a different meta clustering depending on the particular feedback implementation. With the overall idea being that AGN feedback redistributes meta, making halos less concentrated. So let's put in feedback and reanalyze cosmic shear. I'll just highlight one paper here that was the first reanalysis of that kind. Since then, there has been many different ones, and I will only go through a few of them. Otherwise, again, I would use up my whole time. But the basic idea here is that we want to include all those data points that were eliminated by the collaboration. Those are the ones shown with a gray background here. And to do that, of course, we have to now put in a model for feedback effects. At that time, we did something fairly basic. We just used a library of different simulations, checking how they modulate the matter-power spectrum, and build a PCA on that. After, again, lots of simulated analysis, we concluded one PCA should be enough, given the constraining power of DSG1 at that time. So we put it in our model, and let me talk you through the resulting constraints. Orange here is the DS baseline analysis, throwing out of small scales. In green, we do the wrong thing, like Anthony did, including small scales without baryon model. So of course, that's biased. If we then include our baryon model in all small scales, we remove the parameter bias and find something that's consistent with the baseline analysis. But unfortunately, in this case, we also don't really gain constraining power. That can be somewhat improved by putting in more informative priors, but I don't need to talk about that in detail here. Let's just briefly talk about what different people find about feedback. In this case, in a PCA-based analysis, we have to just relate our posterior on baryon feedback to different hydrosimulations shown here as vertical lines. And this analysis of DSG1 down to 2.5 arc minutes preferred something around Bahamas of T.676 to T.78. This turns out to be quite consistent with findings from HEC in year 3. Again, power spectrum suppression, red are their constraints compared to a bunch of different hydrosimulations. So this epoch, and with that amount of constraining power, different data and baryon models found consistent constraints from weak lensing alone. Now, data is getting better. Recently, decade, so that is an extension of DES using DEChem, resulting in, at the end in a sample of 270 million galaxies. So quite some increase in constraining power. Now finds somewhat different matter-power spectrum suppression depending on which baryon model they use. So that's definitely something to work on in the future. The main thing I want to highlight, though, here is that here we just have discrete models, which then in the end would just result in different contours. So we end up with this family of constraints, which is rather unsatisfactory. So figuring out really how to marginalize over these different parameterizations will be important to, at the end, arrive at one set of constraints with error bars that incorporate this systematic uncertainty from different parameterizations. Of course, weak lensing is not the best tool to really probe what the baryons are doing. Here we only measure the impact on the matter-power spectrum in projection, mixing a bunch of scales. So that's the motivation then to combine weak lensing with other probes that measure baryons more explicitly. And the first paper along that line was combining weak lensing with X-ray and KSZ, and all combined. We can already see in these early contours here from not so constraining data how weak lensing by itself does not need as strong feedback as when you then include X-ray and KSZ. That was the first step. Since then, there have been a lot of different probes included in these types of analyses. And I will just highlight a few papers here that were quite recent, using different types of data combinations. Yeah?
So on the previous plot, you're able to constrain better the effective baryon feedback. If you then pull this information into your cosmological parameter analysis, do you then recover some of the information, like some more information, because let's say your PCA modes are better constrained, for example?
I don't remember if they did it in that paper. But right behind you are two of the leading experts who can show you plots how this then feeds back into the cosmic shear analysis. And yeah, I don't remember the number. Can you just say what the improvement was? Yeah. Yeah. So this is now expanding to use a bunch of different baryonic observables, KSZ, gas fraction from X-ray observations, TSZ both at a field level or at a two-point function level, and in terms of mass-Y relation for clusters. They've all find much stronger feedback than cosmic shear alone, with slight differences. And putting them all into one coherent model that really can confront them will be one of the important next steps, because each of them, of course, is sensitive to different redshifts and different halo masses. So one should not just directly compare the suppression of the matter power spectrum, but we need to think about the selection function for these different feedback effects. All right, other avenue, combine more probes. Here I just briefly want to highlight cluster counts in a different analysis than what I showed you before. Now not using the small-scale mass calibration, but using large-scale cluster clustering and cluster lensing to basically determine the mass-observer relation through the bias, halo bias mass relation. And that's an effort really led by Chunhao To, who has now applied this to DES year 1 and year 3, and finds cosmology consistent with other DES probes. That's a great step for optical cluster cosmology. But getting this right really required a lot of work again on the MOCs. That's why I'm highlighting this here. Now, to really do this at DES year 3 accuracy, Chunhao spent a lot of time developing what he now calls the cardinal MOCs. That's the continuation of Buzzard. And particularly important for these projection effects was then the detailed treatment of orphan galaxies, which really are important to understand how many galaxies there are associated with a cluster. So that is at the end then the validation on cardinal MOCs. Cardinal MOCs shown here in the blue contours. From those we have only 3, so that's hard to assess. But again, we can only test what's in the MOCs. There's still a bunch of systematics that we cannot include in these MOC catalogs at the moment, so we need to test them again on synthetic data. And I just want to highlight our laundry list of different effects, where we really start out by writing down the analytic model. And in each step, it was just writing down the basic relation, and then starting to fill it in with astrophysics to be very explicit about when we're making a choice. And then testing each of these choices at a time. And of course, you will need to repeat those tests again and again if you move from just clusters plus galaxies to clusters plus 3x2 point to also including external probes. Because as your data gets more constraining, these systematic biases may become more relevant. So lots of things to test. In the end, we then, of course, get cosmology constraints. As I said, they are consistent with other probes from DES. And the main thing I want to highlight here is the comparison between not including cluster abundance, shown in blue, versus including cluster abundance. So what we learn here is that we really gain information from the mass function, which has different parameter degeneracies than galaxy clustering. So it's not that we're using clusters as an additional tracer in a multi-tracer analysis canceling cosmic variance, but we're really using the halo mass function. Then the next direction, beyond doing more different probes, we can also look at different statistics of the same tracers that we've been already analyzing. And of course, that's a big topic. I will just flash here some contours from current generation relensing analyses. Of course, there's many more. But again, I thought I would show one example from HSC, in this case, the scattering transform, then from DES year 3, which is moment, in this case, I chose moment and wavelets, and peak statistics from KITS 1000, where in each case you can see that adding these beyond 2-point function or beyond power spectrum statistics increases constraining power. And we already heard about Simbig yesterday, who showed some impressive first constraints for a range of statistics from galaxy clustering. So here they analyzed about 10% of the Boss CMAS volume, which was limited by the Quixote simulation volume, and then did like-to-like comparison to other analyses, which were repeated on the same CMAS subset. So here you can see a Simbig power spectrum, including nonlinear scales, compared to EFT power spectrum for that same subset of CMAS, the nonlinear bispectrum, and the CNN example. So clearly, yes, people are starting to extract information from higher order statistics. But Simbig also identified a bunch of modeling and validation challenges that the field will need to tackle in the future. And that will become even more relevant with the next generation of surveys. Because the volume high number density means that we will measure these higher order statistics with much more significance. And in some cases, they will basically have more signal to noise than the power spectrum. And of course, the big question is, are we ready? And this is really then driven by the computational challenges and modeling accuracy. So I think that rather than asking how much information is there in the field or in all higher order statistics combined, the practical question we should be asking is how much of it can we practically extract in light of systematic effects and computational limitations. So far, I've basically only talked about DES. I still want to give a shout out to the DESI collaboration, who of course has done amazing work, not just in terms of expansion history, but also constraining a growth of structure from the full shape power spectrum, where I'm of course showing the very impressive cosmology constraints. But much more, I want to highlight these two tables from one of the supporting papers, showing all the kinds of systematic uncertainties that they quantified, and the different families of mocks that they used in those tests. And Will and Joe DeRose can probably tell you more about all of these. I just want to highlight this is an enormous body of work in terms of supporting papers and a lot of validation that needs to be done. But at that point, it's only done at the 2-point level. So we can't just say, well, they've done it. Now we take the data and say they have fiber collision model and apply it to higher order statistics. There is a topical group on alternative clustering methods doing exactly this testing and gearing up for beyond power spectrum analysis of DESI. Enrique Payas and Carol Quester have been leading a lot of this effort. And they've built a consistent pipeline for simulation-based emulators of 12 different summary statistics, shown up there from the projected 2-point function and 2-point function multiples to then bispectrum density split, a minimum spanning tree, over density PDF, cumulant generating function, Minkowski functionals, wavelet scattering transform, the void galaxy cross correlation function, and the void size function. And for all of those, they are then using Abacus mocks populated with an HOD to build an emulator of the summary statistics. They have been going through validation on both HOD and beyond HOD mocks, so far without observational systematics. But they are really gearing up to the year 1 analysis, where accounting for imaging systematics and fiber collisions still are some unsolved research problems. So this is far from trivial. And just to, of course, also show the promise that they find with this forward model, here are some MCMC results from a single snapshot comparing just the 2-point statistics in gray to various subsets of the other statistics. So there may be information. The question still is whether we can actually use it in light of observational systematics. And that brings me then to the question of what does it take for you to trust higher order statistics at the same level as 2-point statistics? And yeah, that's quite a laundry list. We will probably want these analyses to be blinded. The covariance is a big issue, unless, of course, you're doing implicit inference. We may not really have analytic cross-checks, unlike some idealized cases that we can do for Gaussian statistics, say on Gaussian mocks with a linear bias power spectrum. And then, of course, all the null tests will be very difficult to generalize from 2-point to different beyond 2-point statistics consistently. And I could, of course, talk more about validation on that front. But given the time, I will jump to my conclusions. So we are now in an era where multiple survey collaborations are delivering consistent cosmology from different cosmological probes. And it's largely consistent, with some, of course, possibly interesting cracks in the model maybe emerging. I really want to emphasize here that these key cosmology results are supported by a large number of methods papers, and those are really essential. In order to, at the end, make sense of results, especially when they're surprising, a clear validation plan, and then traceability and interpretability of the results are likewise essential. And of course, if this validation relies on mocks, then the mocks need to be carefully constructed. If it's not in the mocks, you can't test it that way. Finally, on the topic of validation, I want to emphasize this validation is specific to a given survey, data vector, and model. So if you validated one data vector for lambda CDM, that doesn't mean you validated it for WCDM, for example. And the more constraining analysis will typically have more stringent requirements and may also pick up previously unknown systematics. So that's why you find that many of these contours shrink much slower than 1 over square root of survey volume. Simply because if we use the same model, then your Kmax will decrease as survey volume increases. And of course, the whole community is excited about the high signal to noise in the non-perturbative nonlinear regime and in beyond 2-point statistics. We've seen really interesting early results, both from clustering and reglensing. And the challenge for the coming decade is to see how much of that we can really convert to cosmology constraints. And I really look forward to learning more about that from you guys. Thank you.